Hey everybody, this is Miss Berry. In this video, we're going to go over section 3.1, which is called Relations and Functions. So first, let me tell you what a relation is, and then once we do some examples with relations, I will tell you what a function is. So a relation is defined as a set of ordered pairs, and when we're referring to a relation, oftentimes we'll be asked to find the domain and range of that relation. The domain, you've probably heard these words before, domain and range. The domain is the set of the first coordinates of the ordered pairs, and the range is the set of the second coordinates of the ordered pairs. So, for example, let's say that we had just something really simple like this set of ordered pairs 1, 2, 2, 5, and 3, 7. So we could call this relation, we'll just call it R. And we could find the domain of R. So again, it says it's a set, so that's why we're going to put it in curly braces because it's a set. And it says the domain is the set of the first coordinate, so it would be 1, 2, and 3. So 1, 2, and 3. They just so happen to be in order from smallest to biggest here. They don't have to be, as long as you get each first coordinate in there. It doesn't matter what order they're in. The range is the set of the second coordinates of the ordered pairs, so that would be 2, 5, and 7. So pretty easy to find the domain and range of a relation. Let's look at an example from the homework. We're going to go ahead and number this. We'll just call this number 1. It says determine the domain and range for the relation. If you remember, this is called set builder notation. So again, this is called set builder notation. It says that R is equal to the set of all the x's and y's, so it's the set of ordered pairs, such that, remember that long straight line right there means such that, so the set of ordered pairs x comma y, such that x is an element of the integers and y is an element of the natural numbers. So this little fancy z here represents the integers, so z represents the integers. And this little fancy n here represents the, sorry, I could have wrote that neater. Let me try again. A little bit better. That represents the natural numbers. Natural numbers, also called counting numbers. These are the numbers like 1, 2, 3, 4, 5. Integers are positive and negative whole numbers and 0. And then this little symbol here means is an element of. All right, so a few symbols there that you may not have seen before. And again, this long straight line right here. When we're reading that out loud, it's read as such that. All right, so we have the set of ordered pairs x comma y such that x is an element of the integers and y is an element of the natural numbers. All right, so remember the domain, that's what they're asking us to find the domain and range. So the domain of R and the range of R. All right, so the first coordinate here is our x's, and it says that all of our x's are elements of, that means they're just members of, or they come from the integers. So the domain of R would be the integers. And the range of R, remember that's the second coordinate, which is y. And it says that all of the y values are going to be elements of, or they're going to come from the natural numbers. So the range of R, which is the second coordinates, would be the natural numbers. This is a great question for a test. Let me put a little star beside it. All right, so great question for a test. Maybe I'd just say something like determine the domain, and then you have to tell me that the domain is the integers. All right, so let's talk about functions. So functions are special relations. And let's read the definition. It says, a function is a relation in which every element of the domain is paired with exactly one element of the range. All right, so that means that you're not going to have any x values that repeat. So for example, let me show you an example of something that is a function and then something that isn't a function. Let's start with something that isn't a function. Actually, let's write that as not a function. That's probably better grammar. So not a function. So let's say we have this set of ordered pairs 1, 2, whoops, let me go. 1, 3, and then 2, 5. All right, so this is not a function because every element of the domain, that's the x coordinates or the first coordinates, every element of the domain should be paired with exactly one element of the range. And here, the domain element 1 is paired with both 2 and with 3. So 1, the domain element 1 is paired with both 2, and then here we see it paired with 3. So that means that it is not a function. Now that example that I came up with before, I think we called it R, which was 1, 2, what do we do? 2, 3, and then 3, 7. I mean, maybe that was a 5. Anyway, this works. Here you can see that you don't have any of your first coordinates that repeat, which means that every element of the domain is paired with exactly one element of the range. And then it says equivalently, a function is a relation in which no two distinct ordered pairs have the same first coordinate. So again, the first coordinates should not repeat. All right, then we have this section here for the vertical line test. You've probably heard of the vertical line test before. Usually, I will just abbreviate this VLT, so I don't have to write the whole thing out. So vertical line test, VLT. The vertical line test is a way that we can determine if a graph is a function. So this says that if a vertical line passes through, let me fix that. If a vertical line passes through the graph more than once, then that graph is not a function. Sorry, my handwriting's so sloppy. It says if a vertical line passes through the graph more than once, let me change this word right here. I want to change that to a graph. Sorry. Excuse me. If a vertical line passes through a graph more than once, then that graph is not a function. So let's do an example again of something that is not a function, and then something that is a function. So here's an example of something that's not a function. All right, so let's say that we had a function that looked like this. All right, so here's an example of something that does not pass the vertical line test. If you draw a vertical line, you can see it's passing through this graph more than once. It passes through the graph here, here, and here. So it passes through 3 times. So that is not a function. not a function. Now let's look at something that is a function. Vertical line test is very useful. All right, so let's say that we had a graph that looks like this. This is a square root graph. This is totally fine. Anywhere that you draw a vertical line, it's only going to pass through one time. That indicates that this is a function. So there's nowhere that we could draw a line and have it pass through more than once, which indicates to us that this is a function. Is a function. I almost always put a question about this on the test. So I'll ask you something like, use the vertical line test to determine whether the graph is a function. So hopefully that will be easy, as long as you can remember what the vertical line test is. It says, excuse me, consider the following relations and determine if they are functions. Then determine the domain and range for each relation. So just want to point out, even if a relation is not a function, you can still find the domain and range. So domain and range is not specific to functions. You can find the domain and range of any relation. All right, so let's look at this first graph. This is a circle. And what do you guys think? Is this a function? This is definitely not a function, right? Because if you drew a vertical line through here, let's pick another color. Let's do purple. If you drew a vertical line through here, you can see, well, let me not put arrows on it. I just want to put a vertical line here. You can see it passes through more than once. So this is not a function. This is not a function, but we can still find the domain and range. So I'm just going to write D for domain, R for range. Now, I want to talk about finding the domain and range of a graph. Sometimes finding the domain and range of a graph can be tricky, maybe if you're not like a visual person. So let me give you some tips. I'm going to just scoot over here a little bit for finding the domain and range when you are working with a graph. All right, so finding domain and range of a graph. All right, so the domain, you can think of the domain as the x values. You're going to look at the graph on the horizontal when you're finding the domain. And for the range, you're looking at the y values. At the beginning, we called this the first coordinate, the second coordinate. Here I'm using x and y. You can see they've defined those variables. X is our horizontal axis. That's our first coordinate. So x is our first coordinates, and then our second coordinates are y values. All right, and here you're looking vertically on the graph, and I'll tell you what I mean by that. So here you're looking horizontally. I guess we could have wrote horizontally instead of just horizontal. So for the domain, you're looking horizontally, and the range, you're looking vertically. All right, so when you're writing the domain and range of a graph, you're always going to use interval notation, which we know, like I said before when we were talking about solving inequalities. We're always going to use interval notation, which means like parentheses and brackets. All right, let's look here. All right, so we're looking horizontally for the domain. So we're looking, how far to the left does this graph go? How far to the right does this graph go? So the farthest it goes left is right here. The farthest it goes to the right is right here. All right, so if we're counting over, this would be 1, 2, 3, 4, 5, 6. All right, so the farthest to the left that it goes is 2, and the farthest to the right that it goes is 4. So we know that this graph, the x values go from 2 to 4. Now you need to determine if you're going to use parentheses or brackets. The only time you're going to use a parentheses is if you see like an open circle here, say like this, maybe at the very edge. Let me erase this line. So let's say that maybe at the very edge, there was something like this, like an open circle right there. If you saw something like that, that would indicate that you need to use a parentheses. We don't see anything like that here. So if everything looks normal, then you're going to use brackets. Right, so you're almost always going to use brackets here. Now let's look at the range. Remember the range, we're looking vertically. We're looking up and down. Let me use a different color here. All right, so we're looking how far up does it go and how far down does it go. So this is the farthest that it goes up. So we'll draw a straight line there. This is the farthest that it goes down. So let's count. This would be 0, 1, 2, 3. All right, so it starts, we're going again. Anytime you're using interval notation, you should be writing the numbers smallest to biggest. All right, so the smaller number is 0, the bigger number is 2. This graph goes from 0 to 2. So from 0 to 2. We don't see any open circles or anything that would indicate that we need to use parentheses. So we're going to use brackets on the end. Awesome. All right, let's look at the next example of a graph. All right, this is a square function. Or excuse me. Yeah, I guess you could call it a square function. It's really a quadratic function, which we'll talk about soon. This is also called a parabola. All right, so first of all, we have to determine, is this a function or not? We're going to use the vertical line test to determine that. So anywhere that you draw a vertical line here, it's only going to pass through the graph once. That tells us it is a function. So we're going to say this is a function. Now we need to find the domain and range. Oh, and it's helpful to know if a relation is a function because it being a function comes along with a lot of special properties that make it useful to us to know that, or it makes it easier for us to do certain things. So it's useful for us to know if a relation is a function for those reasons. Excuse me. All right, so let's think about the domain. The domain, we're looking left to right, we're looking horizontally. All right, so it says that this graph is just going to keep going. That's what these arrows at the end indicate. Just tells us that the graph keeps getting wider and wider and higher up and higher up. So as this graph gets wider and wider, it's just going to keep going all the way out here to negative infinity. And as the graph gets wider, as the x values get bigger, it's going to continue all the way out here to positive infinity. So these little arrows here tell us that the domain is going to be negative infinity to infinity. Again, that's what those little arrows on the end tell us. And we know from solving inequalities that you always use parentheses around infinities. All right, now let's do the range. Range, we're looking up and down. So how high up does it go? How far down does it go? All right, so let's use a different color. This graph is just going to keep going up and up and up forever. So it's going to continue up here to positive infinity. So that's the highest that it's going to get. The lowest that it gets is right here at 3. Remember, we're writing this from smallest to biggest, so that's why the 3 goes on the left. So 3 is the smaller one, infinity is the bigger one. And again, we don't see any weird like open circles down here, so we know we're going to put a bracket around 3. Infinity always gets a parentheses. Okay. All right, so we will talk more about the domain and range of a graph. This will keep coming up throughout the semester, and we'll get plenty of practice with finding the domain and range of a graph. The next thing I want to talk about is function notation. So function notation is traditionally written as f of x. So you read this f of x. Here f is just the name of the function, and x is your variable. This is the number that you're plugging into your function. So it's the variable, it's the number you are plugging into your function. So traditionally we use the notation f of x, but you could see any combination of letters. Maybe you could see like r of t, g of, I don't know, a. So any combination of letters could be used for function notation. All right, this is number 3. It says, consider the following relation. Oh, and I had one more thing I wanted to mention up here, sorry. Function notation, this is just a fancy way of writing y. So f of x is just a fancy way of writing y. So what this says here is that f of x is equal to y. So that means you're going to take your x value, you're going to plug it into your function, and that's going to tell you the y value. Okay. So let's look at this example. It says, consider the following relation. Rewrite the relation as a function of x. So what that means is that we want to get y by itself, and then we're going to rename. So let's write that down, what we're going to do. We're going to get y by itself, and then we're going to rename, or let's say it this way. We'll say replace. We're going to replace y with its fancy name, f of x. Okay, so let's work on this. Looks like the first thing we're going to need to do, looks like all we're going to have to do is just move this little y over. So let's subtract y from both sides. I forgot to read this to you, but it says negative 4x squared minus 3x plus y equals 2y. Sorry about that. All right, so those cancel out on the left-hand side. You're left with negative 4x squared minus 3x equals 2y minus y is y. All right, and then I'm just going to switch the order here. Typically, we see y written on the left. So just switching that around to match up with what we're used to seeing. And now I'm just going to replace y with f of x. That's its fancy name. And we're done. All right, so if we say we ended up with something here like, I don't know, 5y. Whoops, I wrote it. So say we ended up with something there like 5y. At that point, we would have needed to divide both sides by 5 to get y by itself. All right, so if you end up with a coefficient on y, just divide both sides by that coefficient so that you can get y by itself before you replace y with f of x. I think this has a part 2. Yeah. Okay, it says, or this is like a part B, I guess. Evaluate the function found in the previous step at x equals 2. All right, so we're just going to take our function here. We're going to plug in 2. So we're going to replace that x with 2. We're going to do the same thing on the right. So that would be negative 4 times 2 squared minus 3 times 2. All right, so I think we can solve this in our heads, but you're welcome to plug it in your calculator. So this would be negative 4 times 4 minus 6. So that's negative 16 minus 6, which is negative 22. All right. So evaluating the function just means plug in this number into your function. Evaluate just means plug in. All right. Here we have the difference quotient. If you go on to take calculus, this difference quotient, you do nothing but calculate this difference quotient for like several weeks in calculus. So this is the difference quotient. If you've heard of like the limit, this is part of the definition of a limit. So it's f of x plus h minus f of x over h. So this is just going to give us a lot of practice with function notation. I typically don't put something like this on the test. Like I wouldn't ask you to find a difference quotient on the test. It's not terribly difficult, but it is a lot of arithmetic type of stuff. So let's look at an example. I think this is going to be number 4. These are kind of fun. You'll see why, what happens whenever we calculate this difference quotient. It says, given the following function, determine the difference quotient, f of x plus h minus f of x divided by h. And here's our function. This one is not going to be terribly difficult because we're working with a really simple linear function here. But the more complicated this function is, the more complicated it is, or the harder that it is to find the difference quotient. All right, so I'm going to write down the difference quotient, f of x plus h minus f of x all over h. All right, so the first thing I'm going to do is I'm going to go over here to the side. I'm going to do a little bit of scratch work, and I'm going to find f of x plus h. So I'm going to do that off to the side. That way I don't have to worry about rewriting this fraction every time. So I'm going to take my function f of x, and everywhere there's an x, so everywhere there's an x, I'm going to plug in x plus h. All right, so everywhere there's an everywhere there's an x, I'm going to plug in x plus h. So that's going to be 5 times x plus h plus 4. If you want to, we could go ahead and multiply this out. That's what I would do. Just save yourself some writing over here. So go ahead and multiply through by 5. So just distributing there. All right, so that's 5x plus 5h plus 4. All right, now let's go back over here and plug it in. All right, so that f of x plus h, that whole thing, we've just found that that whole thing is equal to 5x plus 5h plus 4. So this whole piece right here gets replaced with 5x plus 5h plus 4. All right, then we have a minus f of x. We already know what f of x is. They told us what it was. They said that it's 5x plus 4. Now I'm going to do something here that's really important, and I want you to do it too. So when I write in f of x, I'm going to put parentheses around it. And those parentheses are going to just help me remember to distribute that negative. All right, so all of that is over h. All right, so all I did there was I took f of x and I replaced it with what they told me f of x was, which was 5x plus 4. So they told me what f of x was. Whoops, I didn't mean to delete that f. There we go. Now we need to distribute the negative. So go ahead and distribute that negative there. Remember how we talked about before, you could put a 1 here if that helps you. You're really just multiplying through by a -1. So actually, let's write it down underneath it. Let's go this way. All right, so 5x plus 5h plus 4, that's going to stay the same, minus So that's going to be negative 1 times 5x is negative 5x. Negative 1 times 4 is negative 4, all over h. All right, now here comes the fun part, or at least I think it's fun. You cancel out the cancel out what you can. So we have a 5x and a negative 5x, or just 5x minus 5x. So those two cancel. And then you also have a positive 4 and a negative 4. So those cancel. So that always happens with the difference quotient. A bunch of stuff cancels out. You're left with 5h over h. We're almost done, but what is the last thing you see that you could do here? You cancel out those h's, right? Those cancel. And you're just left with 5. Isn't that cool how it goes from looking so messy, like what we had up here? That looks so messy. And then we get down here and it's just equal to 5. I think that's kind of fun. All right, so that's an example. Excuse me. That's an example of finding the difference quotient. All right, so I think we're almost done. Oh yeah, our last thing we're going to talk about is super, super important. This is something that we will continue to use for the rest of the semester, so I'm going to highlight it. All right, so this is really important. Make sure you write this stuff down. So this is very important. All right, so finding the domain of a function. Let me get them all three. There's 3 rules for finding the domain of a function algebraically. So that's what we're going to be doing here. They're going to give us a function, say like f of x equals 3x squared plus 5x minus 7. And then we will algebraically, which means without having to use a graph, we will find the domain. I'm going to erase that because that was just an example of a function. All right, so we have 3 rules for finding the domain of a function. As we write these down, you're going to want to take a second and pause the video and finish writing in what you need to. It says, if a function is an even indexed radical. All right, so let's talk about what that means. The index of a radical is that whatever number is right here. So that's the index. Remember the stuff that's under here is called the radicand. The actual little check mark looking thing, that's the radical. And then this number here is called the index. All right, so if you have an even indexed radical, you can think about these are like square roots. Let me zoom in a little bit. So my writing is a little bit easier to read. Square roots, fourth roots, sixth roots. Of course, the most common ones you're going to see are going to be those square roots. But any even indexed radical, here's what you do. You set the radicand, which is the expression that's under the radical. You set the radicand greater than or equal to 0 and solve. So that's going to tell you your domain. All you do is you just set your radicand, which is the expression under the radical, greater than or equal to 0 and solve. The reason for this is because you're not, or when you take the square root of a negative number, that is an imaginary number, which we haven't talked about yet. And so we do not want to consider the negative roots. So we just consider the positive, which is the greater than 0, and the equal to 0. So we're just considering the positive and the equal to 0 parts. So pretty easy. Let's look at the second rule. It says if the function is a fraction with a variable in the denominator, very important, this last part, with a variable in the denominator. All right, so if you have a fraction and it's got, or we call them rational expressions in math. It's just a fancy name for fraction. So if you have a fraction with a variable in the denominator, you're going to take your denominator, you're going to set the denominator equal to 0, set the denominator equal to 0 and solve. And then one extra piece here, this tells you what to exclude from your domain. Those are going to tell you the spots where the fraction is undefined. All right, so when you have an even index radical, you set the radicand greater than or equal to 0 and solve. And I could add in a little extra part here. It says this tells you what to include in your domain. And if you have a function that's a fraction with a variable in the denominator, you just take your denominator, you set it equal to 0, and you solve. And this is going to tell you what to exclude from your domain. All right, those are the most two important rules. This last rule just says for all other functions, the domain is all real numbers. All right, so that means, and there's a couple of ways that you can write all real numbers. Some books you'll see them write it as like this little fancy R, and some books will write it in interval notation, just as negative infinity to infinity. So for all other functions, that means the only two functions that we have to worry about are even indexed radicals, like square roots, fourth roots, sixth roots, and fractions where we have a variable in the denominator. All right, so let me put all three rules on the page at one time. Maybe you can take a screenshot of this. Like I said, these rules keep coming up throughout this class. Or the questions where you have to find the domain of a function will keep coming up. So it's very important that you know these rules. All right, now let's look at a couple of examples of finding the domain. I think I try to do at least one of each type here. Okay, so we have number 5, find the domain of the function. We have f of x equals 12 over x minus 14. All right, so you may have to take a second, pause the video, and write this stuff down. All right, so f of x equals 12 over x minus 14. This function is a fraction, and it has a variable in the denominator. So we're using the second rule here, which tells us to take our denominator, set it equal to 0, and solve. This one's an easy one. All we have to do is just add 14 to both sides. It's going to cancel out on the left. And we get x equals 14. But remember, this is telling us what to exclude from our domain. So there's a couple of different ways that you could write this. The easy way to write this is to use what we called earlier set builder notation. All right, so the easier way to do this is to use set builder notation, which I'm fine with on the test. But you could also use interval notation, which I want to think that's what your homework uses, but I'm not 100% sure. All right, so this is what the domain would look like in set builder notation. Let me just add ourselves a note here. We're going to say we want to exclude this value from our domain. And remember why that is. we want to exclude this value from our domain, because if we plug in this number, see what happens if we plug it in. That would be 14 minus 14, which is 0 down here in the denominator. And remember, we're not allowed to divide by 0, so that's undefined. So we want to exclude this value from our domain because it's undefined at that point. All right, so let's look at the two types of ways you could describe the domain here. I'm just going to write D for domain. So the domain in set builder notation, you would just do this little curly brace. Then you would say it's all of the x's such that, remember that long straight line means such that, x cannot be equal to 14. Super easy. So all of the x's such that x cannot be equal to 14. And my long straight line here was like kind of exaggerated. Let me draw like a normal. That looks a little bit better, not really. Right, so again, that's read as all of the x's, so that means all of the x's such that x is not equal to 14. So that means any x value is okay except 14. Now, interval notation. I'm just going to draw a little number line to help you with this. So every number is okay except for 14. So we have kind of like a little, you know, we're shading this side because all those numbers are okay. Do a little parentheses there. And then we also have a parentheses this way. We're including all of these numbers. And we're using a parentheses here because we do not want to include 14. If we use brackets, that would be including the number 14. We're using parentheses, so that means we're not including that point. All right, so this would be out here at negative infinity. Goes all the way up here to 14. Close parentheses. We got a little gap there, so gap, we use the union. Open back up at 14 to infinity. So those are two different ways you can write the domain of this function. I'm fine with either of these on the test. Obviously, set builder notation is easier, so that's the one that I would use. All right, we have a couple more here. Part B says f of x equals negative 4x squared minus 3x. Now, let me tell you, the most common mistake I'll see people do here is they'll set this equal to 0 and try to solve it. Remember, you're only doing that for fractions that have variables in the denominator. Remember these rules. It told us that the only time we have to worry is if we have a function with an even indexed radical, or excuse me, a function that is an even indexed radical, or if we have a function that's a fraction with a variable in the denominator. All the other functions, the domain is really easy to find. It's just all real numbers. All right, so let's look at this little guy. I'm trying to zoom in. It's not letting me. There we go. Okay, so let's look at this function. F of x equals negative 4x squared minus 3x. This is not a fraction. This is not a radical. So the domain is all real numbers. We're just going to do negative infinity to infinity. Again, you could also use this little fancy R, or you could write out all real numbers. No work to do here. It's super easy. I always put a question on the test where you have to find the domain. So make sure you know these rules. All right, then we have, struggling with my zoom here. Okay, there we go. This will work. We have f of x equals the square root of x plus 7. Then on the outside of the radical, we have minus 3. This is a square root. That's an even indexed radical. So we're using that first rule, which says you take whatever's under the radicand. Here, that's x plus 7. All right, so here, that's x plus 7. And you're going to set that greater than or equal to 0, and then you're going to solve it. We do not care about this minus 3 out here. All we care about is what's underneath that radical. So x plus 7 is underneath the radical, so that's what we care about. We're going to solve this now. We get x by itself by subtracting 7 from both sides. Cancels out over here. You got x is greater than or equal to -7. And now we just need to write this in interval notation, or again, you could use set builder. Here, interval notation is actually easier. All right, so there's our little number line. It says it's all the numbers that are greater than -7. All right, so all the numbers that are greater than -7 would be this way. This would be the numbers that are bigger than 7. And we have an equal to under our inequality here, so we're going to use a bracket. Right, so now we can easily put this in interval notation. And we have our shaded area starts at -7. It goes all the way out here to positive infinity. Infinity always gets the parentheses. We already determined that -7 had a bracket. So there you go. That's the domain. Now, on this last one, originally, I had put x equals 4. Now, I took it off because look at my directions. My directions said find the domain of the function. Now, this does not work here because x equals 4 is not a function. If you remember, this is one of our special lines. It's actually a vertical line. So think about if we had a vertical line at x equals 4. That would be the x values. This is the y values. All right, so this would be our relation here, or our line, our equation, x equals 4. Does this pass the vertical line test? It definitely does not, right? I mean, if you draw a vertical line straight through here, it's going to hit through like, you know, an infinite number of times. So this is not a function. So it really doesn't even fit the qualifications of this question because the question said, find the domain of the function. So this is not a function, but you could find the domain of it. You still could. Here, the domain is just, you know, if you think about it like in terms of finding the domain of a graph, remember it's the horizontal. So how far to the left does it go? How far to the right does it go? It only includes the number 4. So literally your domain would just go from, whoops, try that again. It would just go from 4 to 4. That would be your domain here. And those are brackets. That kind of looks round, but it's actually a bracket. So the domain is just one number, just goes from 4 to 4. In set builder notation, that would look like this, x such that x is equal to 4. So that's 2 ways you could write the domain of that function. Or excuse me, the domain of the relation. Whew, close one. So that is not a function because it does not pass the vertical line test. All right, you guys, that is everything for this video. Please let me know if you have any questions or if you have any, if you're struggling with the homework, let me know and I'll be happy to help you. Otherwise, I'll talk to you guys soon.